Welcome guys to today's class. In today's video, we want to discuss thermodynamics. It's an important topic in the field of chemistry. And so we will start with the definition and other important concepts of it. Unlike chemical kinetics, which we have posted on our channel, thermodynamics discusses the feasibility of a chemical reaction. Recall we said that chemical kinetics discusses the rate of chemical reaction. So thermodynamics discusses the feasibility of a chemical reaction. It has several laws, such as zero law, first law, second law, third law. But in this video, we will be concentrating on first and second law. That is what we'll focus our discussion on. Now, let's discuss these laws we just mentioned. Under the first law of thermodynamics, it states that energy can neither be created nor destroyed, but can be transferred from one form or place to another. I repeat, energy can neither be created nor destroyed and can be transferred from one form or place to another. Let's understand this concept very well. Before we continue, we need to understand the word universe is equal to system plus surroundings. Universe equals to system plus surroundings. What do we mean by this? Look at a system. We'll call this a system, for instance. Okay? The totality is called a universe. Anything outside this system, which is inside this universe, is called surrounding. Now, let's understand the concept of the first law very well. Energy can neither be created nor destroyed and can be transferred from one form or place to another. Look at what it means. If the surrounding loses energy to this system, let's say the surrounding loses 3 joules of energy to the system. The implication is that the system will gain it. And so nothing is what? Created, or nothing is what? Destroyed. No energy is created, no energy is destroyed, because the energy that is meant to be destroyed from the system, from the surrounding, was gained by the system. And so it was useful there. So it was not what? Destroyed. So you neither create energy nor destroy it. Yes. Take again. Assuming that the system loses its own energy to the surrounding, that same thing will occur as well. That means if the system loses 3 joules of energy, the surrounding will gain it and use it. And so it means that the energy that the system felt that he has lost it, the surrounding what? Gain it. So it transforms from energy in the system to what? Energy in surrounding. Are you getting it? So that means energy can neither be created nor destroyed. This is one of the concepts of that first law of thermodynamics, that energy can neither be created nor destroyed, but can be transformed or transferred from one place to what? Another. So once the surrounding is losing, the system will be gaining, and so nothing is destroyed or lost. And once the system is losing, the surrounding will gain it and make use of it. So nothing is lost or what? Destroyed. That is about this. In some textbooks, you will notice that we are told that change in energy or the internal energy of a system is equal to Q plus W. Whereas in some textbooks, you will notice that change in internal energy is equal to Q minus W. Question is, which of these is correct? Both are correct. Yes. It depends on the focus or the concentration, or where the person writing this formula is trying to focus on. It depends on where you want to concentrate his discussion on. If you want to discuss or focus on the discussion of what happened on the system, you will see its own formula. If you want to discuss on what happened on the surrounding, you will have its own formula. Look at what I mean. Assuming that the writer is discussing what happened on system. He will be seeing a lot of formulas concerning the system. Yes, energy, heat energy can flow into this system. And when it flows into this system, the system will gain energy because it's discussing what happened to the system. And so, when the surrounding, this part, perform work on the system will gain work. And so, the internal energy of it will be the heat energy plus what? The work. So, that heat energy will be called endothermic energy because it's gaining the what? Energy. Are you getting it? So, you will be having Q plus W as the internal energy. That means the internal energy of that system will what? Increase. Yes. Now, what if the writer is focusing on system as well, such that it's telling you that the system is what? Heat flows into the system. Heat energy is flowing into the system. Here is plus Q. That is, the system absorbs heat energy. Are you getting it? And also, the system perform work on the surrounding. The system is doing work on the surrounding. Wow. That means the system will be losing energy in terms of work because it's performing work on the surrounding. That will be telling you that change in internal energy will be equals to Q minus W. You have seen where this formula will now come in. You have seen where this one will come in. With respect to system, you notice that it's when work is done on the system and when the system gains heat energy. That is when you will see this first formula. And also, when the system gains heat energy and work is performed on the surrounding by the system, that is, the system perform work on the surrounding, you have the work to be negative. Here, it happen, all this we are discussing happen in our daily life. Yes. Take for instance, for this one, if someone goes to carry a weight, yes, want to carry a weight, you notice that as the person is carrying the weight, scientifically or thermodynamically, we say the person is performing work on the surrounding. Yet the surrounding will be taken to be the weight and its environment. So it's carrying the weight, lifting it up, dropping it, lifting it up, dropping it, lifting it up, dropping it. You notice that at a point in time, you will see the person sweating profusely. Yes, it's sweating because the internal energy of that system is reducing because it's losing energy in terms of work performed on the surrounding. That is typically what you are seeing here. Okay, and so all these things we are discussing, it happens in real life most times. Okay, let's see another one. This is a system because we are discussing what happened to a system. When the system is losing heat energy, we call it minus Q. It's losing heat energy to the surrounding. That means as it's lost the energy, the heat energy, the surrounding will gain it. And so when it also perform work on the surrounding, so you have seen losing heat energy to the surrounding and performing work on the surrounding, you notice that change in E will be equals to minus Q minus W. That means that system internal energy will decrease the more. It will decrease the more. It will be negative. It will decrease more and more. I don't know if you're getting it because this minus this will be negative. Okay? Then, if you are talking about system again, and the system is losing heat energy to the surrounding and also gaining heat from the work, energy from work performed on the work system. If work is performed on the system and the system loses energy or heat energy to the surrounding, you notice that change in E of it is equals to minus Q plus W. You have seen that we can derive many formulas very important to be used when we talk about what happens on system. It's important for you to note that in chemistry thermodynamics, because we also see thermodynamics in physics, in chemistry thermodynamics, it focuses on what happens on system, and that is why you see us focusing on what happens on system. So all these formulas are very important in thermodynamics when it comes to chemistry. So when they ask a question on thermodynamics, these questions are very important. You have to think of it as some of the important formulas you need to know. Okay? Now, since in chemistry it focuses on system, what happens on system, how does it flow, and how is the system performing work or gaining work, energy through the work? we have to now go into types of system. We have basically 3 types of system. Yes. One is open system. In open system allows matter and energy to flow in and flow out. I repeat, open system allows matter and energy to flow in and flow out. What do we mean? Open system, let's say this is an open system. It will allow energy to flow in, matter to flow in, and also flow out. Are you getting it? And so that is about open system. Then when we talk about closed system allows only energy to flow in. It allows only energy to flow in, but matter, it doesn't allow it to flow in. You see it? So it allows only energy to flow in or flow out, but matter, it doesn't allow it to what? Flow in. Anything matter, it doesn't allow it, such as air. Let's say now air, it doesn't allow air to flow in. Air is a matter, it occupies space, so it doesn't allow it to what? Flow in or flow out. So that's about closed system. Then when we talk about isolated system is a system which does not allow both the matter and energy to flow in. Yes, it doesn't allow both the matter and energy to enter or leave. It's important for you to know that in isolated system, we note that change in E is equal to 0. Yes, it's also to note that in isothermally, that change in E is 0, change in T is equal to 0. When something occurs isothermally, it means that the energy is constant, the temperature is constant. Change in E is 0, change in T is 0. And from here, once you have, let's say, this condition now, we have that change in E is equal to Q minus W. That is, it gains energy and it performs work on the surrounding. Take for instance, you now notice that when change in E is 0, we have 0 is equal to what? Q minus W. Therefore, you have that Q is equal to W when this goes the other side. Yes. Note that work, formula for work are many. First times distance. Yes. Yes. Now, another formula for work is pressure times change in volume. Pressure times change in volume. You need to note this. Yes. You need to note this. It will be negative when this system is performing work on the surrounding. Like in this one, work will be equal to minus P change in what? V. Because the system is performing work on the world surrounding. Then it is to be positive when the surrounding, or when the system, when work is performed on the system. It is positive when work is performed on the system, but it's negative when the system performs work on the world surrounding. You notice. Now, since Q is equal to this, now, isothermally, we note that if they ask you to get the work, please don't forget about this formula that work is equal to any RT ln V2 over V1. Yes, and work is equal to any RT ln P2 over P1 over P2. Okay, now how do we change this to P1 over P2 instead of P2 over P1? It's because pressure is inversely proportional to volume. The higher the pressure, the lower the what? Volume. Are you getting it? And the lower the pressure, the higher the volume. So if here is final over initial, here will be initial over the final. There must be inversely what? Related. Okay, and so we need to note about this word formula when we are talking about question on this. Then this formula can be negative or positive depending on if work is done to the surrounding by the system, if the system is performing work on the surrounding. Okay, so note this as you want to solve question on this thermodynamics. Okay, let's see how to solve this question we have. 1 mole of an ideal gas is expanded isothermally and reversibly at 27 degrees Celsius from a volume of 3 dm cube to 5 dm cube. Calculate the work done in kilojoules. Wow. What you do here is, since number of mole is given as 1 and V1 is given as 3 dm cube, V2 is equal to 5 dm cube, then temperature is equal to 273 plus 27 equal to 300 degree watt Kelvin. That means the temperature, we must convert it to watt Kelvin because that is the SI unit of temperature. Okay? R, having noted this, you now have to recall that work done is equal to nRT ln V2 over V1. I have to note this formula. Yes, we are asked to calculate it. What is your N? 1 times R, 8.314 times T. T is 300 ln V2 is 5 all over 3. So, as you have gotten to this point, what you now do is you use your calculator, say this times this, and that will be giving you 2494.2, then times ln 5 over 3. Just use your calculator, ln 5 over 3, 0.551083. So after you have calculated this, so when you say this times this, you'll be getting it in joules, and that is 1274.1 joules. But the question is, get it in kilojoules, and is equivalent to kilojoules means divide by 1000. That is 1.2741 kilowatt joules. We've discussed the first law of thermodynamics, and so we want to discuss the second law of thermodynamics. What does second law of thermodynamics state? It stated that for a reaction to be spontaneous, the entropy must be very high. The entropy must be greater than 0. Yes, entropy should be greater than 0 for a spontaneous what? Reaction to take place. That means for a reaction to occur naturally, the entropy of it must be high. From elementary chemistry, we noted that entropy means the degree of disorderliness. Yes, that means when the degree of disorderliness is high, that means the reaction will be spontaneous. It will occur spontaneously or naturally. For you to understand it very well, take for instance, look at this marker. If I release it from here, it will fall spontaneously. The disorderliness of it will be high. It will fall spontaneously. But look at that marker. I'm holding it down. Can it climb up? No. Unless energy is applied, then it can go up. I don't know if you're getting it. If I apply energy on it, you will see it will go far, because energy means force times what the distance cover. So if I apply force on it, it will cover a particular distance up the hill. Are you getting it? So energy is applied. That means for a reaction to be spontaneous, this will be very high. The disorderliness will be very high. Then that means the reaction can occur naturally. But for a reaction to be reversible, the entropy change should be equal to 0. That is for reversible what? Reaction. So this is for reaction to be spontaneous, and this for reaction to be reversible. That means for this to go down and go up, the entropy change should be equal to 0. Now, from here, we'll talk about the free Gibbs energy, which says that change in G is equal to change in enthalpy minus T change in S. That means for a reaction to occur, the entropy should be very high. And when the entropy is very high, we say that the reaction will occur spontaneously or naturally, right? So when the entropy is high, this free gives energy will be negative. I mean, it should be less. And once it is less, it's trying to tell you that change in entropy is very high. I don't know if you're getting it. Once this is very high, this will be very low because it will be giving you a negative answer. So this will be what? Very low. That means for a reaction to be spontaneous, the free gives energy should be negative and entropy change should be greater than 0. That is positive. This is two conditions that will make a reaction to be very spontaneous. But for a reaction to be reversible, that means this is 0. This times is 0. This minus is 0. For reaction to be reversible, this will be equal to change in enthalpy. That is for reversible what? Reaction. You get it? This is when the reaction occurs spontaneously or naturally without anything called force or energy applying or making it to what? Occur. That means it will occur naturally. Raise something from up, down, it just fall easily without you applying force. But when it is down, for you to go up the hill, you will notice that you apply force to or energy for it to occur. And so for it to occur from down to hill, it means you are trying to make this falling down of this object to be reversed or reversible. That is moving up as well. That is this now be equal to 0. But if it is only for it to move from up to down, it occurs spontaneously. Say this is greater than 0, and so this will be negative. But for this one, this will be equal to change in enthalpy. That is, it means that this is 0. That is why this is equal to enthalpy. These are the concepts of the what? Second law of thermodynamics. Yes, that for a reaction to occur spontaneously, this is greater than 0. But if a reaction wants to be reversible, this should be equal to 0. Now, let's go and solve this question. To solve question number 1, a gas absorbs 2,500 joules of heat energy and expand from this to this at a constant pressure of 480 here. And they say how much work is done by the system. How much work is done by the system? Wow. To solve that question, what we will do is that since the gas absorbs 2,500 joules, the implication is that Q is equal to 2,500 joules. It's positive. And it expands from this 3 liter to 7 liter at a constant pressure of 4. Okay, the work is equal to P change in V, right? Correct. Where the P is 4, the change in V is 7 minus 3, 4 liter. 7 liter minus 4 liter is 7 liter minus 3 liter is 4 liter, okay? And so we have it to be what? 16 atm liter. This is 4 atm times, so 16 atm liter. That is this. Now, since this is the work, note that 1 atm liter is equal to 101.3 joules. It's a relationship, conversion relationship. 1 atm liter is 101.3 joules. And therefore, 16 atm liter will be equal to, when you cross multiply, you have 16 times this, and that will be giving you 1620.8 joules. This is equivalent. So this is 1620.8 joules. But recall that they said, look at the system. We say in chemistry, focus is on system. The system, how much work is done by the system? If the system is doing work, it means it's doing work on the surrounding. And so this work will be what? Negative. Minus 1620.8. Then this system absorbed 2005. It absorbed 2005 energy. So energy absorbed is plus Q. It will have positive energy, but in terms of work, it will be negative because it's performing work. It's the one doing the work. Are you getting it? Therefore, change in internal energy should be equals to Q. Q is positive 2500 minus how much work is done by the system minus 1620.8. Now, when you use your calculator, you have 2500 minus 1620.8. That will be giving you 879.2 joules. Yes. But if they said how much work is done on the system, it means that this work is going to be positive. That is, the surrounding is doing the work on the system. But because they say how much work is done by the system, that is how we say that the work is negative. So we go to question number 2. So question number 2, calculate the change in internal energy if the system absorbs. So look at our system. If the system absorbs 300 joules of heat, is absorbing 300, and perform 300 joules of work, is performing on the surrounding. When it's performing work, it's going to lose that energy, minus 500. Therefore, change in internal energy, this, or change in E, whichever one, is equals to plus 300 minus 500. That will be giving me minus 200 joules. For the second one, if the system absorbs this, okay, for the second, the system is absorbing 720 joules of heat, and the surrounding perform 300 joules of work on the system. Wow, the surrounding is performing work on the system, so the system will gain that energy. So change in energy, that is internal energy, will be equal to 720 plus, because this is plus 300, and that is 1020 joules. That means the energy or the internal energy of that system must increase because it's high, it's positive. Then we go to question number C. If 400 joules of work is done on the system and the system loses 225 joules of heat. Wow. Now for question number C, we said that this system is losing 225 joules. It's losing energy now. Then the system is losing, so the arrow should be out. It's losing heat. Then the work is done on the system. Work is done on the system, so the system will gain that work plus 400. Therefore, change in E is equal to minus 225 plus what? 400. And that will be giving you 175 joules. So that is 175 joules of what? Energy. That will be this is for question number C, this is for A, and this is for what? B. We'll go to question number 3. The standard heat of formation of methane, carbon dioxide, and water are minus this, minus 74.9, minus this and this respectively. Calculate the standard enthalpy of combustion for methane. Standard enthalpy of combustion simply means the change in enthalpy of that system when 1 mole of a substance is completely burned in oxygen or air at a particular temperature. That is the standard enthalpy of combustion. And so that means I have to write combustion reaction of methane, which goes this way. combustion reaction of methane plus oxygen to give me CO2 plus water. This is 4, so we put 2 here. This will make it to be, we'll put 2 here. We have balanced the equation. Yes, this is the balanced equation of the combustion of methane. Now, this is for methane 1 minus 74.9. Here is 0. So 2 times 0 because it is not given to us. Then this is minus 393.5, and this is 2 bracket minus 286. Okay. Now the standard enthalpy of combustion is equals to change in enthalpy of what? Standard enthalpy of combustion is equals to change in enthalpy of what? The product. I mean, add up the product's own enthalpy of the product plus the one of, okay, minus the one of what? Change in the one of what? Reactant. Enthalpy of the reactant. So if we add this and subtract it from this, it will give you the standard enthalpy of combustion, which is what we are looking for. And this will be giving you minus 393.5 minus bracket, okay, plus bracket 2 bracket minus 286, then minus this one bracket minus 74.9 plus 2 times 0 is 0. Okay, so this will be giving me plus. So once I use my calculator, say this times this, it will give you an answer minus this minus what this one give you, because this is negative. This times this will give you negative, minus this plus what you have here, then minus times this is plus. So once you compute it, you will notice that what you'll be getting is minus 890.6 kilojoules. You shouldn't put per mole because this mole I've taken it, this is 1 mole. 1 mole times this, it will be in kilojoules. So this is kilojoules, 0 kilojoules, kilojoules, kilojoules. So this is the answer to the question. Thanks for watching the video.